quick recap where we left off last time. We were talking about transient conduction heat transfer. And on the right-hand side of the board are the equations we ended up with for a particular model. The model is called the lumped heat capacity model. It's a very simple model to use, but it's only valid for a certain range of a dimensionless parameter called the BO number. The BO number is H LC over K. LC is a characteristic dimension of the object. If it's a plane wall, you can derive that L sub C equal the half length of the wall. The wall's 2L in thickness. L is the half wall thickness. If it's a cylinder, L sub C is half the outside radius. If it's a sphere, L sub C is 1/3 the radius. In general, L sub C is the volume divided by the surface area for anything. The volume divided by the surface area. So if you use that model, and that model then says that the temperature in a body at any particular time is not a function of geometry, the spatial coordinate. The temperature is not a function of x or r, radius. It's only a function of time. So we use that. We derived a little simple differential equation. We integrated it with the initial condition. We ended up with this equation right here in your notes. Theta is T minus T infinity. Theta I is initial temperature minus T infinity. Rho CV over HAS was defined as something called the time constant, units or seconds if it's in SI. Rho CV over HAS. V is the volume. AS is the surface area. Very simple equation. Exponential decay function. Then you can integrate that with respect to time and find out how much energy has been transferred to or from that particular body. When you're done with that calculation, you have Q over Q naught, 1 minus exponential minus T over tau. This Q naught is rho CV theta I. Here's what it is. Rho times V, density times volume is a mass. This is just mass C times change in temperature. What temperature? T initial minus T infinity. So that term, Q naught, one way to interpret it is the maximum amount of energy that could occur if the process continued all the way out to T approaching infinity. The maximum amount of energy. So it's a ratio. The actual amount of energy divided by the maximum amount of energy. All right, so there we are for the simple model lumped heat capacity. Of course, the next question is, what if the BO number comes out to be greater than 110? Okay, we can't use that anymore. So now we have to go back to chapter 2 and start from there. Now the temperature is going to be a function of x and time, or maybe radius and time if it's a long cylinder. By the way, this is a long cylinder. A long cylinder or a sphere. Now we have to go back to the governing partial differential equation, chapter 2, which is the second partial of T with respect to x squared. This is for a wall. Is equal to 1 over alpha dt d time. In words, left-hand side is the net conduction heat transfer that occurs in the x direction. The net conduction heat transfer in x direction. The right-hand side is the time rate of change of energy stored in the object. Okay. The picture that goes along with this, and we had it on the board last time, but I'll reproduce it here. This is a plane wall. There is a fluid blowing over the outside of the plane wall. temperature T infinity. Convection coefficient is H on both sides of the wall. It's symmetrical, the same conditions. The wall has a thickness of 2 times L. We measure X from the center of the wall, so the center of the wall is X equals 0. The initial condition Ti. We solve that partial differential equation with the initial condition and the boundary conditions. The boundary conditions are, let's take the easy one first. At x equals 0, dt dx is 0. The slope of the temperature curve at the middle is 0. It's symmetrical. Second boundary condition, when x equal L, conduction into the surface equal convection out of the surface. Conduction into the surface control volume equal convection out of the surface control volume, chapter 1. Okay, so you use this, one initial condition, 2 boundary conditions, you solve it, and you get a pretty horrendous solution, yeah. It's an infinite series. We can approximate that. By the first term, if something called the Fourier number is greater than 2/10. So a new dimensionless term, Fourier number. And the Fourier alpha T over L squared. Thermal diffusivity times the time in seconds divided by, for the wall, the half wall thickness squared. If we do that, the equation looks like this. And this is, in the textbook, this is equation 543A. That's the first term of that infinite series. That'll give us a good temperature if the Fourier number is greater than 0.2. Okay. This guy is zeta. And, okay, here it is. The temperature is a function of x and time. X and time. Where is time? Time is in the Fourier number. There's Fourier. There's Fourier. The time is in the Fourier number. Where is x? In the cosine term, x star. What is x star? X star is x over L, the half wall thickness. It's a ratio. X star goes from 0 to 1. What's C1 and zeta 1? They're constants. Where do they come from? Table 5.1. I'm going to put table 5.1 over there because I'm going to use it for an example problem later. So I'll put it over here. This is the format of the table. Plain wall, long cylinder, and sphere. Each of them has a zeta 1 and a C1. So the C1 and the zeta 1 come from table 5.1. And at the bottom of table 5.1, it tells you, I'm going to stretch your name. If it's a wall, we have BO, HL over K. If it's a cylinder or a sphere, BO is equal to R naught is equal to H R naught over K. A sphere, BO, is H R naught over K. All right, don't forget heat transfer number 1. The object is to find the temperature, how it varies with whatever, time or spatial coordinates. Number 2, find the heat transfer. Okay, so the total energy transferred Q integral rho C T minus Ti d volume. Integrate that over the volume with time. This gives Q over Q naught, 1 minus sine zeta 1 over zeta 1 theta naught star. Equation 549. If you want the center temperature of the wall, that occurs at x equals 0. Just put the 0 up here for x star, of course. And that is cosine of 0, which is 1. So theta naught star. The naught means at x equals 0 is equal to C1 exp zeta 1 squared Fourier. And that, let me check where that is in here. Okay, that is equation 544. Okay, I think that's all we have there. Right. Okay, for the plane wall, there are 3 things you can get from this. The temperature at any x and any time. You want the temperature at any x and any time, use this equation. If you want the center temperature of the wall, use this equation. Matter of fact, you can just put x equals 0 here, it doesn't make any difference. But this is a simpler version. If you want the Q, the energy transferred, in joules, use that equation. So, here is the summary for the three. I'll put it right by here. Cannot use this, I'll put it right here. So, plane wall, long cylinder, and a sphere. Plane wall for the center temperature, or the temperature at any x for any time. There it is, equation 543a. The temperature at the center for any time. There it is, 544. Energy transferred. Q naught, or Q, equation 549. Long cylinder, any radius, any time. Center line of the long cylinder for any time. And finally, the energy transfer as a function of time. 552A, 552C, 554. The sphere, the temperature at any radius or any time in a sphere in a transient condition. 553A. The center of the sphere at any time. 553C. Energy transfer to the sphere as a function of time. 555. So pretty much, there's chapter 5 on the right side of the board. That's it. That's chapter 5. Nothing else to worry about. That's all we're going to do. We're not going to do the infinite series. No. That's too complicated. All our problems pretty much, if they don't satisfy the BO less than 1/10, pretty much they're going to have Fourier greater than 0.2. Okay. You need that table 5.1 with these 9 equations. 9 equations. Everything's done with those 9 equations. Over here, only 2 equations. Lumping capacity. Okay. What's the difference in these two guys? I'll put that here and then I'm going to erase, but I'll put it over here first. I'm going to do 2 pictures for you, show you a difference in those 2 on that panel over there. I'm going to look at a sphere being cooled. First of all, the BO is going to be less than 1/10. This is lumped heat capacity model. And then I'm going to look at the actual one, what actually occurs. It's valid for BO greater than 1/10. So here is a sphere. we have a fluid blowing over it at T infinity. This is initial. Ti is 100 degrees. Here's the actual picture. We start off everywhere the sphere is at 100 degrees. No matter where you look at the radius, it's 100 degrees everywhere, the initial temperature. I'm going to just assume that the temperature T infinity is 20 degrees C, 20 degrees, just to put a number in there. At time equal 10 minutes. I'm just making that up, whatever. Okay, here's the picture. Here's the picture. At time equal 20 minutes. Here's the picture. There's the picture. Lump T capacity. Temperature is not a function of x or radius. It's only a function of time. Far right-hand equation. It's not a function of that. The sphere starts to cool down. The outside surface now is 80 degrees. The middle of the sphere is also at 80 degrees. Anywhere inside the sphere at any radius is 80 degrees. I wait longer, it cools down some more. Now, the outside of the sphere is 55 degrees. The center of the sphere is 55 degrees. Any radius in the sphere at that time is 55 degrees. That's the Biot model. Now the real one, if the Biot, let's say, is greater than 1/10, this isn't going to work. Okay, which part starts to get colder faster? Oh, the surface. The surface is exposed to that fluid at 20 degrees. So up here now, I'll assume that's cooled down to 75 degrees. Of course, the center might still be at, like this right here. Let's just say the center in this case is at 100 degrees. Somewhere else, this temperature might be 85 degrees. Wait a while longer, the surface cools down some more. Now the surface is at 50 degrees. The center now is at 90 degrees. And at some particular radius, the temperature is 70 degrees. So that's the difference in the lump T capacity model, which are these three pictures. Temperature is only a function of time, not of radius, versus the non-lump T capacity model. Now the temperature depends on the time and on the radius. Time and radius. Time is in the Fourier. X or radius is over here. By the way, anytime you see an asterisk or star, let's just say star, X star, theta naught star, that star tells you it's a ratio. If it's theta, it's star, it's a ratio. Theta over theta I, it's dimensionless. If it's X star, X over L, it's dimensionless. R star, R over R naught, it's dimensionless. This is dimensionless. The Fourier is dimensionless. The Biot is dimensionless. As I said before, we engineers love dimensionless numbers. Yeah, it makes life simple. What does X star go from? 0 to 1. What does R star go from? 0 to 1. That's why we like it. Okay. Now let's work an example problem. Okay, I'm going to take a long cylinder. It's steel. Diameter 10 centimeters. Let's see what else we know about it. Starts out at 300 K, T initial. 300 K. It's exposed to an airstream at a temperature of 1200 K. The convection coefficient on the outside surface of the steel cylinder is 100. Properties, rho. K. C. And alpha, thermal diffusivity. And we're supposed to, I'll draw a picture of the cylinder here. Here's the diameter. And we have a T infinity blowing over it. H on the surface. And we're supposed to find how long it takes until the center line temperature gets to 800. Temperatures are all in specified degree Kelvin. Okay. Starts out at 300. I don't want my properties at 300. I don't want them at 300 because it doesn't stay at 300 long. It starts getting hot. Matter of fact, it ends up getting up to a temperature of 800. So when I find my properties in the appendix, I want to use something like a T average. 300 plus 800 divided by 2, which comes out to be 550. So when you go to the back of the book and find the properties, find them, interpolate them at 550. All the density's not going to change. There's only one density. But these three guys will. K will change, C will change, alpha will change. So back of the book, with the kind of steel you got, find out what those values are. This is carbon steel, by the way. Okay, now, next step, of course, bio. That's always the next step. Fluid mechanics, you got to flow in a pipeline. First step, always calculate Reynolds number, always calculate. Is it turbulent? Is it laminar? This is heat transfer. Always first step in transient. Check it, BO number. Can I use lump heat capacity or no? Okay, so BO number. HL over K. Not HL, pardon me, R. Okay, R naught, diameter 10 centimeters, radius, half of that, 5 centimeters. And if I do that, there it is, 0.04. Eight. That number is less than 1/10. So we can use lump heat capacity.
Is that with the new properties or the initial properties?
There's only one property. They don't change. Everywhere in every equation, you put these properties which are at the average temperature. Okay, let's see. So, we're supposed to find time. Center temperature, okay? There's the equation right there. T, center temperature. this is T center line. The subscript 0 means at radius equals 0. T, where the radius equals 0, minus T infinity, divided by T initial minus T infinity is equal to EXP minus our HAS rho CV T. Solve for T. We know everything. H, surface area, pi r squared, pi d squared, pardon me. Rho C, V, T infinity, Ti, T center line, put them all in there, straightforward. Solve for T and we get 560 seconds. Okay. So if I look at that model, at 560 seconds, the center temperature has reached 800. The temperature on the outside surface is 800. The temperature at any radius in the cylinder is 800. That's what the lump heat capacity model predicts and says. There's a picture. All right. Now, we're going to check that against the approximate solution. Okay? Remember, the approximate solution is an approximate solution to an infinite series, which is a solution of the governing partial differential equation. Is it valid for this VO number? Well, of course it is. Of course it is. Why don't we just always use it then, if it's valid all the time? Because that thing is so simple. If you can use it, use it. It'd be crazy not to. If you can use it, use it. There's a very small error using it. But if you want to get more complicated, with the Fouriers and the Z's and the C1s, yeah, this is valid anytime as long as, what again? The Fourier is greater than 0.2. Okay. So, now we're going to use the approximate solution. Okay, the approximate solution, we start out and to use the approximate solution, the Fourier has to be greater than 0.2. Here it is. So the first thing I do is calculate the Fourier number. Take alpha, there it is, divide by the outside radius squared, we know, 5 centimeters, times the time. Uh-oh, I got a problem. I don't know the time. So I can't find the Fourier number first. So what do? I assume it's going to be greater than 0.2, and when I'm done, I check it and make sure it's greater than 0.2. Okay, I assume it's greater than 0.2. I can't calculate it right now. Okay, if I do assume that, here we are. This is chapter 5. Everything you can use is on this side of the board, right here. Find it. I can't use that. I can't. I'm going to check it against the approximate solution. These are the approximate solutions. There it is. It's a long cylinder. It's a long cylinder. What do I want? I want the time for the center temperature, 800. Center temperature, radius 0. Oh, there it is right there. That's the equation I want. The equation 552C. Center temperature. There's time. Use 552C. Okay, so we use that, and this is what we get. Beta naught star Okay, get C1 and zeta 1 from table 5.1. Okay. BO. What is it? A cylinder. Okay, here, cylinder. BO. HR naught, 5 centimeters. Over K. So the BO number, 0.0976. Go to table 5.1, find the BO number, interpolate. 0.0976. Go to the cylinder, right there. Get the value of C1, 1.024. Interpolate. Get the value of zeta 1, 0.438. There it is right there. Put them in here. Remember the Fourier, alpha T over R naught squared. Remember what theta a T naught is. Center temperature, 800. Free stream temperature, 1200. Theta I, initial temperature, well that was 300 minus 1200. Put C1 in there, put zeta 1 in there, take the natural log of both sides, solve for time. Time, 915 seconds. Oh yeah, they're gonna be a little different. That guy was 560 over there. Not 560, 560. Let's see here, 560, we didn't get that guy. Oh, no wonder. The time, there's 860. What did I do, 560? That's not gonna work. 860, that's better. Okay. About 6% difference. Which one's a better estimate? Oh, probably this guy. He comes from the solution, the governing partial differential equation. This guy's an approximate one, which gets you a pretty good number if you assume that model.
Why are the BO numbers different?
You've got to be really, really careful because there's what I used to find out if I could use lumped heat capacity. BO number. Here's what I used. If I go to table 5.1, they both say BO number. Why are there two different BO numbers? Because the guy that wrote table 5.1 said, if you want to use my table, this is how you define the BO number. You know, I play cards, I'm the boss of the table, okay? I'm dealing you. That table came from him. He can call BO whatever he wants. Why wouldn't he call this? Well, this way you don't forget things. If it's a cylinder or a sphere, it's just a radius. Over here, you got to remember. Let's see. If it's a cylinder, it's the radius squared. Pardon me. It's half the radius. If it's a sphere, it's a third the radius. Why make life difficult? Well, that's because this is how the BO number is really defined. And that LC is defined as a volume over the area. This is the right, correct way to do it. But to make life easy, this guy said, I'm just going to put an R naught for both these guys, so you don't have to worry about is it divided by 2 or divided by 3, and use my table, and you get the right one. It's his call. He's in charge. He wrote the table. He can do what he wants. If I want to use it, I have to do what he tells me to do. He says, if you want to use my table, there's a new BO number, which is this one. Isn't it like the old one? But does that bother you? I say, well, kinda. Well, it's okay. You get used to it.
So the R naught for the first view number should be 0.025 there.
That's right, that's right, that's right, yeah,
All right.
yeah, that's right. Now, let's say part B of the problem says, at this time, next, at t equal 915 seconds, what is the surface temperature? Okay, there's chapter 5. Go back there again. What do I have? I have a long cylinder. The BO is not less than 1/10. Where do I go? Long cylinder. What do I want to find? Here it is. The temperature when the radius is r outside and the time is 915 seconds. What equation? 552a. With r star, there'll be an r star in there. R over r naught, that is 1. Wherever you see an r star in that equation, put 1. Solve for temperature at r equal r star, at r equal r outside, pardon me. And time equal 915 seconds. And if you do that, you will get the surface temperature of 819 degrees K. So here's the picture for that. At time equal 915 seconds, the center of the sphere has reached 800 degree K, but the surface now is at 819. And you can compare the two to see the difference. When we use these approximate equations, the temperature depends on not just the time, but the radius. When you use lump heat capacity, the temperature does not depend on radius, only on time. Okay, so we worked them both ways now. Oh, by the way, some people and some textbooks also use a graphical approach. Rather than use these equations, these 9 equations here, they give you a series of 6 graphs. 2 graphs for this, 1 for temperature, 1 for Q. 2 graphs for this, 1 for temperature, 1 for Q. 2 graphs of this, 1 for temperature, 1 for Q. And you could read the graphs, not too accurately. There's so many lines on them, it's very, very hard to read accurately. But they are available. They used to be in our textbook. The author pulled them out and put them online now because he doesn't use them anymore in the textbook. It's hard to program graphs. You can't do it. Try and program the movie chart. You don't do that. You get curve fit equations for all the friction factors. So it's probably better to look at the equations. They're fairly straightforward, you know. They can be programmed where they're called the Heisler charts. Heisler charts. Transient conduction problems. Okay, I think that's got it. So that ends chapter 5. We're going to start chapter 12, radiation, on Monday. Okay, so next week we start. You can work problem 4 2 ways. One way I worked it here using table 3-4. You need one more? Yeah, okay. Or you use table 3-5, which is the fin efficiency. So either way, use table 3-4, like I did here for part A, or use table 3-5 for part A. For part B, you've got to use table 3-4 for part B, the temperature. Okay, so if you can look over that and see how you did compared to that. The average was pretty decent, 78 and a half. 78 and a half. The high was 1/100, 2 at 98 and a half. So the three highs, 1/100, 2 98 and a half. When we get these back to you, we're done for today. We'll see you on Monday. Let's see, that's section 1.